Okay, I'm going to go through the answer to this problem set that I gave out in class on November 6th, and we're going to begin with question 2 here because question 1 was done during class on November 6th. So see the after class PowerPoint for chapter 11 to look at the answers for question 1. All right, so here's our assignment on question 2. We're going to use para-ethylbromobenzene as the source compound for each of these 5 compounds right here. We're going to use sodium acetylide or any Diels-Alder dienophile as the extra carbon source. You might notice that 2 of our compounds right here, oops, sorry, let me get the draw feature. Yeah, so right here, this compound and this compound both have additional carbons in them. Okay, sorry. Yeah, I got to remember that I have the touch screen here and not to use the touch feature to move the thing here. All right. Okay. All right. Okay. So let's look at this problem here and what is it telling us that we need to do? Okay. All right. So our source compound is going to be para-ethylbromobenzene. Let's just draw that. Okay. All right, so here's para-ethylbromobenzene. All right, so we probably recognize that the conversion here is just simply one step, right? That we're going to treat this by some sort of vigorous oxidation reaction. We'll say KMNO4. Heat, or this chromium reagent, Na2Cr2O7. Aqueous sulfuric acid and heat. Either of those are good reagents for turning any alkyl benzene that has benzylic hydrogens into the corresponding carboxylic acid. Okay, recognize that in this next one here, we're now going to be looking at this one. We don't have a direct way to remove 2 hydrogens. All of the alkenes that we've seen so far in the class either come from elimination reactions or from partially hydrogenating an alkyne, and this is really what we're going to make this one by an elimination reaction. Okay, all right. So let's look at how we're going to do that. Okay, so we need something that can be eliminated. We can either take an alcohol and dehydrate it, or an alkyl halide and do an E2. And since we only know how to replace hydrogens with halogens, we're going to do the E2 route. So we're going to treat this with NBS, which is now the preferred reagent for benzylic bromination. And that's going to produce this compound right here. And when we do an E2 reaction, let's just say NaOET, that's going to take us to the other product. Okay, all right, so that's the second product. If you look at the third product, and there's a clue here that all of the other products come from this one. Okay, so the third product, you can sort of see that this is really just the ozonolysis product of this, right? Okay, so we're just going to do an ozonolysis to that. And that's 3 out of the 5 compounds that we have to synthesize. Okay, the other 2 that I've circled, we have to add extra carbons. Recognize that we're going to be adding we need to add a carbon here. And most additions of carbons that we've seen so far are going to involve using alkynes in some way. Okay, so let's think about how we're going to do this. Okay, we either have to turn this into an alkyne, or we're going to take advantage of something in the directions here that tells us to use sodium acetylide as the source of extra carbons. So if we use sodium acetylide as the source of extra carbons, this problem becomes a lot simpler, because now all we have to do is turn this into something that has a leaving group at the point where I said add carbon here. Okay, so we're going to just treat this with anti-Markovnikov hydration. Okay, and that's going to, sorry, I'm trying to get used to this in tablet mode. Okay, and that's going to give us the alcohol. Okay, so it's easy to turn an alcohol into a leaving group. We'll just treat it with tosyl chloride and pyridine. Okay, and this is going to give us this. Okay, sorry, it looks like I'm running out of room here. I got to plan better here. All right, so sodium acetylide. Okay, I've lost the bromine here too, sorry. Yeah, okay, so the bromine needs to be here. All right, and as you can see here, we can add the two carbons that we need with the sodium acetylide, right? Okay. And that gives us this. And we're going to need to reduce it, so I'm just going to say H2, and Lindlar's catalyst is going to take us to the end. Now in the space here that is remaining, I'm going to be drawing the transformation that we need to think about here. Okay, so we have this compound, and we need to think about how we're going to transform it into that other product, which is this compound here, and we have the directions that we can use any dienophile as a source of extra carbon. So that is really accounts for our extra carbons right there. Okay, so let's think about how we're going to now do this. Okay, this is, of course, is going to involve at some point Diels-Alder reaction. And what I've circled in here are the two carbons that we're going to add as a dienophile. Okay, all right, so let's think about how we're going to do this now. If we're going to do a Diels-Alder reaction, we need a diene, and this is not a diene right here. This needs to have another alkene. Okay, so we're going to need to put another alkene group in here. Let's just treat this with NBS and light again. Okay, there's a question here about the selectivity, but we're going to see in a second that it's not really going to matter that much. Because whether we're doing allylic bromination or benzylic bromination, gives us something that we can use to do an E2. Okay. So it doesn't matter if we get one or both or the other. Either of these is expected to do an E2. To make the requisite dying. Recognize that this is merely the Diels-Alder product from this and an alkyne that has two cyanide groups on it. Okay, so let's redraw this so that it looks like it's ready to do the Diels-Alder reaction. And I'm going to abbreviate that aromatic ring AR for aryl. Okay, and what you'll see here is that when we do the Diels-Alder reaction, that produces our product. Okay, alright, so that's all those compounds. Let's now look at the next one. Alright, the next one is a HOMO-LUMO question, and we're supposed to place all of the pi electrons into the correct orbitals to represent the ground state of this molecule, 1357 octatetraene. Okay, and let's go ahead and do that. I'm going to shift this over here, try to get it all on the screen. Okay, so if we look at the pi electrons, there's 1, 2, 3, there's 5 alkene groups, so there should be, 4 alkene groups, so there should be 8 pi electrons. So let's just put them in the lowest energy orbitals, 2 at a time, 2, 4, 6, and 8. And we're supposed to identify the HOMO. Remember, HOMO stands for the highest occupied molecular orbital. And that's this one. This is the one that's of the highest energy, but has some electrons in it. So this is the HOMO right here, orbital number 4. LUMO stands for the lowest energy unoccupied. That's what the U stands for. Okay, and that's number 5. That's the lowest energy orbital we have that doesn't have any electrons in it. So this is the LUMO. Okay, let's look at these other questions it's asking us over here on the side. Alright, so we're looking at what's the LUMO if we put 2 more electrons in it. Okay, so if we put 2 more electrons in it, that means that we would be filling orbital number 5. And that shifts the HOMO and LUMO definition up by 1. So the HOMO is now orbital number 5. And the LUMO is orbital number 6. Okay, we imagine that we're hypothetically putting 2 electrons right there. That's what this compound represents. Alright, this compound below it represents taking 2 electrons out of the system. Okay, so we're, and let's imagine that we're taking the 2 highest energy electrons out. That would be the ones at number 4. That means number 4 now becomes unoccupied, and that's the LUMO, and the HOMO is number 3. If we took these 2 electrons out, number 3 would be the highest energy orbital that has electrons in it, and number 4 would be the lowest energy orbital that doesn't have any electrons in it. Okay? Alright, let's look at this one. We're going to write a mechanism for a couple of reactions here, and in both of these, resonance is kind of a big part of this. Let's take advantage of the directions that tell us we can use H+ here, and let's go ahead and do that. Okay, so protonation of the alcohol. Gives us this compound, and we're going to lose water like we've done quite a lot of in this course, and that's going to give us, put a methyl here, carbocation. Recognize that this carbocation is flanked by two alkene groups, therefore it's allylic on either side, and thus it has a resonance form that we can write. And that's this resonance form right here. Okay, so what I'm doing is I'm just shifting that alkene there and moving the site, or moving the p orbital that doesn't have any electrons over to the end. We can do that. That's just a resonance form. It's changing the location of electrons without changing the connectivity. Okay, at this point you can see that our ring size has increased from 5 to 6. This is where we can now do a 1,5 alkyl shift. Sorry, 1,2 alkyl shift. Like that, and that gives us the proper ring size. Okay, the carbocation is now here. Okay, recognize that any thing that comes along and pulls this proton off, it's actually a very favorable thing to have that happen. I'll just have the sulfate anions since it's going to be a catalyst here, and this is going to produce this. Recognize that in the product you have a benzene ring, and in the starting material you have no benzene ring. And thus this should be a tremendously thermodynamically favorable process, right? Okay, let's look at this one. And again, it's also starting off similar to the previous one. We're protonating an alcohol. Okay, here the chloride ion is actually going to be quite important. And that's producing this protonated alcohol, and this will now lose water. Okay, I'm going to draw the carbocation here, and recognize that the first product there is simply the product from that carbocation reacting with a halide ion. Alright, so this carbocation, because it's adjacent to a pi-bonded system, is actually stabilized by resonance, however, and we cannot ignore the fact that there is a resonance structure we can write for this, and that involves an allene system. Okay, so that's a resonance structure we can write. We often represent this C here as a dot. Okay, and that's what this dot in the structure means, so you know that there's an actual carbon there, and not that it's an extra long carbon-carbon double bond. Okay, all right, so it's a cumulene system. And in this resonance structure, you can see how it's possible for the chloride to attack here, and this is going to produce this other product right here. So this is how we get this. This is just a classic example of like the allylic carbocation, except now there's a triple bond, and we call this system here the, instead of allylic, it's the propargylic. Okay. Cation. Okay, all right. All right, now let's look at this final last structure here. We're supposed to provide a structure for compound A and explain or predict the endothermicity or exothermicity of each of the steps of the reaction. All right, we're saying that this is a Diels-Alder reaction here, and recognize that this substructure here is, of course, a dienophile. It looks like we have some extra CH2 groups here, and these are the linker CH2 groups, and they seem to be right here in the product. Okay, so the Diels-Alder reaction that we're looking at would really make these two compounds. We can look at it in a retro sense like this, and thus the structure for A is kind of an interesting compound. And this is the compound that you see here. All right. And if we look at the Diels-Alder reaction, that would be this, okay? And it looks like what we're doing here is we're thermally opening the cyclobutene ring, and that's a type of paracyclic reaction that we would talk about in a graduate level class, but you can sort of see that the arrows I've shown there more or less connect the arrows to the compound A. All right, let's think about what's happening in each step. If we look at step number 1, this step, it lowers angle strain. But the system isn't aromatic. We're going to say that this one is more than likely endothermic process. Let's remember the values that we quoted for angle strain back in chapter 3 were much less than the energy from gaining an aromatic ring system. So this is probably going to be an endothermic process. Okay. Now, if we look at this one, we see lots of good things happening. But most importantly is that aromaticity is restored. We'd probably say that this step here is exothermic. And if we look at the overall reaction, of course, what we can see is that we made two new carbon-carbon sigma bonds. We relieved angle strain, and we didn't really affect the degree of aromaticity. So we probably say that overall it's an exothermic reaction. Okay, so it's probably very thermodynamically favored. Okay, so this is the end of this one, and I hope all I'm doing is just verifying the answers that you already got on your own anyway. Okay, so I'm going to have to turn this into a non-tablet, okay, to stop the recording, and